and we'll be very happy to have you in future events. So now we move on to the second talk of this particular morning session, which will be by Dr. Shiv. Faculty of College MTTS Kerala chapter, and I think actually MTTS ABS Kerala chapter. So Professor Anu Mohammed, please take over the virtual podium and introduce the speaker.
Thank you, sir. Thank you, Chinmay Saha, sir. It's a didn't need any introduction. He's
Crowded place.
Sir, I am not in a crowd. Your friends may be there, sir.
So then you really need a mask?
Okay. Okay. Sir, Dr. Shiv Narayan obtained the PhD degree in electronics engineering from Indian Institute of Technology, Banaras Hindu University, Varanasi, India in August 2006. He is electromatics of CSIR since he is holding the position of principal scientist at CSIR NAL. Earlier, he held the position of scientist B in SAMIR, Society for Applied Microelectronics Engineering and Research, Kolkata, India, during the period March 2007, May 2008, where he was actively involved in the array antennas. Particularly in field of electromagnetic applications, and the topics include frequency selective surfaces, radar absorbing surface, radome, metamaterials, numerical methods in electromagnetics, antennas, pattern synthesis of antenna array, and EM material characterizations. Particularly, he is working on the design and analysis of FSS structures based on advanced numerical techniques, that is GSM, transmission line TMM, and FDTD method for 8 years. Dr. Shiv Narayan is the author or co-author of over 100 technical documents, including peer-reviewed journal and conference papers. He has published technical briefs with Stringer on various topics such as FSS technology for the design of high-performance antennas and FDTD modeling inside microwave. Dr. Shiv Narayan was awarded with Excellence Award in Research for the year 2018-19 from CSIR NL for significant contributions to the electromagnetic design and development of FSS structures for airborne applications such as radomes, RAS, and antennas. Recently, he was awarded with the prestigious CSIR Raman Research Fellowship for the year 2019-20 and visited College of Engineering, San Diego State University, USA. He is reviewer of several prestigious international journals published by IEEE Transactions on AP, IEEE and Wireless Propagation Lectures, IEEE MTT, IEEE Sensors, Elsevier, Cambridge University Press, Springer, Nature and Technology Science, Press, etc. He is a life member of ISAMP. We welcome you, sir, for the second talk, and obviously our student will have to will be talk, sir. Over to Shiv Narayan, sir. Shiv Narayan, sir.
Sir, you are not on mute.
Shiv Narayan, your audio is not.
I think now it is okay.
Not there. Yeah, now it's fine.
Yeah, thank you, Anu Mohammed, for introducing me in front of audience. And first, I will thank you to Dr. Sudhakar Rao for arranging this workshop as well as inviting me, and Professor Saha for taking care of all the arrangements and everything, and Shiv for uh, becoming the host and that helping in that actually whatever workshop is moving on. And Arjit Mitra, I am on to thank you to him. So my talk is on basically on FSS technology, what is going on right now for the radome, RIAS and antennas. So I will presentation and share the screen. So is it visible to all people? Hello.
Yeah, it is
Yes,
visible. It is visible. You can
yes,
go
yes.
ahead.
Please
Yes, sir.
confirm. I
Yeah,
think now it is
it is
fine.
visible.
Okay, thank you. Thank you.
Yeah, right.
So shall I start?
Yeah, please go ahead.
Okay. So my talk is associated with the introduction that the introduction about the center and then fundamentals of FSS technology. Basically, CSIR NAL first is aircraft design and development and development of new generation Hansa aircraft. And third is the stealth technology program, whatever it is going on for the DRDO and ADA. So NL is also supporting the stealth technology program in going at the country level. So Center for Electromagnetic that was established in June 1990, led Dr. Rakesh Mohan Shah. When it was established, so several activity we have right now: design and development of airborne radome structure subsystems like airborne radomes, including stealth radomes, low RCS air intake ducts, low RCS fuselage, and antenna sighting for low RCS, active RCS reduction, design and development of radar observing material in structures using frequency selective surfaces, metamaterials, graphene and CNT. And also we do the design analysis of conformal structures, atmospheric electron selection. So to support all this activity, we have EM Design Center, experimental microwave facility we have for material characterization. We have microwave anechoic chamber that was established in 2002. And we have PCB etching machine for fabrication of metamaterial and FSS structures. For measurement of for material characterization, we have a facility where we can go up to 170 gigahertz. Of FSS structures, we have the facility where we can do the measurement from 2 to 40 gigahertz. We have adaptive antenna facility where we can measure in X band. So these are the national facility what we have at our NAL. Electromagnetic material application facility we have 0.2 gigahertz to 170 gigahertz. FSS based design and development facility we have from 2 to 40 gigahertz, and adaptive antenna facility. So till now we have developed several radome, design and develop radome at NAL for the national requirement. For example, we have designed and developed and certified Jaguar variable thickness radome. That TOT was transferred to IF and HL in 2008. and certified Radome, Saras nose cone Radome, that is certified in 2000. This was developed for NL Saras aircraft. Multi-octave Radome TOT transferred to Indian Navy. Apart from airborne Radome, we developed several Doppler weather Radome. Like for ISAW, we have developed, this is close to 20-meter diameter. And also we have developed some ceramic Radomes. So these are all our sponsor to whom we support for the design and development, like Boeing USA, DRDO, CAPS, ADA. These are our sponsor to whom we do the work. Now we'll come on the topic frequency selectivity. The origin of FSS has started the periodic structures due to the great potential of military application. The oldest patent concerning the periodic surface was issued in 1919 to Marconi and Franklin. In 1968, a patent was filed by Professor B.A. Monk on periodic surface for large scan angle. So Professor B.A. Monk, when he has started as a part of PhD program, and he has started working on periodic surfaces and all these things. After his work on that, the periodic structures given the name of frequency selective surfaces. So in that way, we can say the Professor B.A. Monk, he is the father of the frequency selective surfaces. After his work, lot of research is started going on frequency selective surfaces. Previously, it was basically used for the radome application, dichroic plate for the deep space application. Recently, FSS find several applications for like we have medical application, antenna application, radar observing structures because of its filter characteristics. FSS basically is a 2D periodic structures of either metallic patches filter characteristic depends on the what kind of structures we are using, that may be band pass passive. And for example, we have given a cross aperture FSS here. If you see the brown color, it is a copper. Actually cross aperture. So these are all the apertures. The structure behaves whenever electromagnetic incident upon it, it behaves like a band pass. So this is the transmission band associated with reflection band. So in this case, we generally prefer the copper for the metallic screen, because copper is easily available, as well as melting point is very high for the copper, so we can use for aerospace application. The types of FSS we can divide into two types based on the element geometry. There are two type element geometry, that is the patch type, where the metallic patch will be printed in 2 dimension with the periodic configuration, and aperture type, this basically reflect the signal whenever signal incident upon it. Second is the aperture type inductive FSS transmit the signal. Basically this aperture type FSS, whenever wave incident upon it, it behaves, it allows the pass across this. FSS characteristics, there are 4 kind of FSS characteristics, like low pass, that is a pass type FSS, so the low pass, and high pass it so square aperture kind of, and band stop it so like pass type single square loop, and aperture type square loop it so the band pass characteristics. So based on the frequency characteristic, we can tell there are 4 type FSS structures. Standard FSS structures available in the literature, like single square loop that show band reject filter, band reject characteristics at the design frequency like 10 gigahertz, and double square loop structures because it is made up of 2 single square loop. So inner one resonates at higher frequency, and outer one resonates at lower frequency. They combine and it show the band pass. associated with two band reject filter characteristic. And frequency. And we can design the FSS into the three different configurations are there for the designing, like a free standing FSS where there is no dielectric support. It can be considered like a suspended in the air. If you want to realize, we have to make the support of foam and PU foam and this kind of structures. And single layer FSS, the FSS that is backed by the dielectric, these structures and associated with the FSS structures on other side. And cascaded FSS structure, this is made more FSS layers and separated by the dielectric spacer. Basically, this is used to enhance the bandwidth of the FSS structures. So these are all the design configuration of the FSS, how to design. So this design depends on our requirement, where we want high bandwidth or low bandwidth. It depends on that. So there are several methods for the design analysis of FSS structures. Like during 17 and 18, it was used conventional methods like equivalent circuit model, transmission line, transfer matrix method. So these methods gives very good insight into the physical problem, and also this is easy to implement and it takes less time to get the result. The only the drawback is there whenever we go for arbitrary kind of shapes, so it is difficult to analyze with equivalent circuit model, because it is difficult to produce the equivalent circuit model for arbitrary kind of structures. So to solve such kind of problem, the full way method is more suitable because it's and the current distribution. So it is easy to calculate the field across arbitrary kind of shapes, and that the only drawback is there whenever we solve large problem, it takes more memory and time. So in that case, approximate method is more suitable, like high frequency method like geometrical optics, physical optics, GTD and UTD. So these methods are approximate method we call high frequency methods. So for electrically small problem we cannot solve because error will be more. So in that case, recent whatever methods has come, like hybrid method. For example, we have physical optics method and MOM and MM and GSM method of momentum, GTD method. So these methods take care of electrically small as well electrically large problem. Basically like a radome kind of structures, where radome at the nose side has a high curvature region and electrically small portion, and if you go to the bottom side it is electrically large and curvature is less. So in that case we can use both low frequency as well. So there are several applications of FSS. It has um, actually demanded application in the area of aerospace engineering and for designing radome, RAS, antennas, all these things. And for interference also it is used. Modern building and locomotive also it is getting used, like in modern building where the walls are made up of glass and that. So if you want to make the available wireless communication inside the building, so we can make band pass FSS structures and print over the glass. So it will allow the signal at mobile, whatever signals are there, it will allow inside the buildings, rooms and that. And also it is used for locomotive like metro rails and that. We can use FSS structures to allow the signal to easily pass without any losses. And this is also used to block the signal into the building. Like if you want to make the building like where some strategic work is going on, where no radar can detect what is going on inside and signals. So in that case, we can embed the FSS structures like band stop FSS structures into the building wall. So in that case, it will not allow the signal what actually is really required to block the signal. So in Israeli already has implemented the FSS based building where no signal can transmit in the restricted area. And high power microwave system, the FSS structures can be used for high power microwave system like autoclave, microwave oven, all these things to reduce the leakage at 2.4 gigahertz that cause the problem to the users. And same for medical instrumentation like in MRI also, whoever the operators are there, they are very close to the MRI system. So there also radiation happens at 2.4. So we can use the FSS like a band stop, so it will not allow the signal to go out of the instrument. But here, as we belongs to the aerospace area, so basically the talk will be on radome antennas and radar observing structures. The why we are using for FSS for all these structures, the reason.
Hello, sir. Hello, sir. Your voice is not audible as well as screen is also not sharing, sir. Shivada, could you able to see the screen?
No, sir, I think he has some network issues.
Okay, okay.
Hello,
Hello, sir.
We can hear you.
hello.
We can,
Are you able to hear
sir, we
me?
can hear you as well as we can see your screen also, sir.
Okay, okay. I think laptop got discharged. I'm sorry for that. Now shall I start?
Continue, sir.
Okay, okay, fine. I will start. So we was here the aerospace application. So FSS has several application in aerospace like radome antennas and RAS. The main reason why we are using FSS for all these application because it enhance the performance of the device within the frequency band and it also reduce the outer band RCS of the device. That is the basis for the stealth application of FSS. So nowadays FSS becomes more popular because of the stealth technology going on worldwide. Yeah. Now we'll go first for FSS for Radome. So basically Radome be characterized
Sir, are you there, sir? Hello?
Hello, sir.
Shivada?
Yes, sir. I think connection is lost again.
Okay. When sir comes now, I think his video can be switched off so that more bandwidth may be obtained in that case.
Yes, sir. Yes, sir.
Hello,
Hello, sir.
hear me?
Yes, sir. Sir. Sir.
Uh, con- that uh, for this is the FSS based Radome. Advanced. The novel hybrid based FSS structure. So here the FSS structure is designed with one single square loop where some cross is associated. So here single square loop that resonates
Hello, sir. Shivada,
Hello, sir. I think it's lost again. Maybe I'll tell him once he arrives.
when sir comes, you please convey sir to switch off the videos. Sometimes it may help us.
Yes, sir.
Sir, Chinmay sir. Chinmay sir.
Yes, what is the problem? Could you talk to Dr. Shiv Narayan?
Sir, actually I don't have his contact, sir.
You are also not audible. You should be a little bit louder.
Okay, sir. Okay. Sir, I
So,
think he came back.
pardon?
I think he came back, sir.
Okay. Dr. Shiv Narayan, you are there? Dr. Shiv Narayan,
Sir, I can't see his name in the list.
do you have his phone number?
No, sir.
You don't have.
Might be logging in again.
So if you let me see, I think I might have his number. So what I would suggest is to connect from dual devices. One may be mobile, another from laptop. So this may be WebEx related issue also. So Sivanta, I think you have his number because you emailed, right?
Yes, sir. I emailed him, but I don't have his number. I think I have his mail ID, but
No, why I am supposed to have his number, but I'm not having. Anyone is having his number?
Hello, I'm Raghavan.
Oh yeah, Professor Raghavan.
I will give his number.
Can you call him and suggest him to connect from two devices, maybe one mobile, another laptop?
Oh, okay, sir. Okay, sir.
Yeah, yeah, please.
Hello. Hello. Sir, I am Raghavan. Dr. Chinmaya Saga suggests that you use both mobile and laptop. Both, if you use, it should be possible.
Yeah, mobile can be used.
No, that's why he's suggesting to use mobile. Mobile, it is possible.
Yeah, mobile can be used.
Okay, sir.
Yeah.
No, you use mobile, sir. Okay, sir. Okay. Hello, sir. Saga, sir.
Yeah, yeah. Please tell me.
I will tell his number also. 96.
Okay, just one second. Srivata, can you also note down?
sir, I got his number.
9686
968.
869
Yeah.
3341.
Yeah, Professor sir.
You are back? Yeah. Dr. Sivnaran, are you back? We see you are connected, but we don't see you or hear you as of now. So sometimes from certain devices, some this type of issues happen. So one of the solutions we have seen is to connect from using two devices. One of that you can use only for audio. Maybe your mobile can be used only for audio. Yeah, yeah, yeah. That would be good, please.
Good morning, Sudhakar Rao, sir.
Good morning, Professor Raghavan. How are you?
Fine. Very happy that you are organizing everything from India, staying in US and doing everything from India. Great thing.
I'm not organized. You guys are organized.
Virtual organizer.
I'm only
along,
helper.
I was
along with
wondering.
along with Dr. Chinmaya Saha.
I'm just a helper. So I'm
I
not a
was
doctor.
searching him in the morning session. I was searching for your name, Professor Raghavan, in the morning session.
Oh, it is in the name of God.
Oh, again you are in God mode?
No, no, no. I don't know. My computer person has named as God.
Fine, God and EM exist everywhere. So no.
Yesterday I saw your sweet child also in the photograph.
Yeah. She was here and she wanted to be on my lap for some time. Then I told, okay, this is the chance.
Future antenna engineer.
Same thing I want to say. Let her also come into metamaterial.
No.
Ephesus.
I just think real. Yeah. So in between, maybe audience, you may, if you have any queries and you have anything like you want to in general ask, you can ask because we have Dr. Rao, Professor Raghavan, and Dr. Karthikeyan, Dr. Prasad. So in
Dr.
general, research.
Dr.
Yeah,
Krishnagant also is here. Who
yeah,
can tell
Dr.
about
Krishna.
Krishnagant?
Yeah. Yeah,
Krishnagant
you may talk about your experience.
on your Ephesus structures.
Hello, good morning, sir.
Krishnagant?
Sir, good morning, sir.
Yeah, please stand on your video.
You please tell about your Ephesus to our research scholars.
No, don't tell. I think you start presenting.
Correct.
Yeah, you can present a few slides in the meantime.
Right.
Are you there, Krishikant?
Hello, sir.
Yeah, start presenting. The speaker now.
No, present. If you want to change, please.
Sir, I'm not yet prepared. I don't have my slides ready.
Yeah.
available with me.
You don't need to share the slides, maybe. You can just talk on your journey on FSS. And you have done some fantastic design and have good quality publications and some real application. So you may talk about your journey for 5 minutes by the time we get back, Dr. Shiv Narayan.
Yes, sir, and I'm happy to tell that I worked with Shiv Narayan, sir, in CSIR engineer in 2015 and 16. And currently I'm working with Dr. Prasad at ADA. Now I joined ADA recently and I'm here in Nada.
Hello.
Yeah, Dr. Shiv Narayan, you are back.
Hello, sir.
Yeah, the talk is over. I think Krishnakant took over. So
Actually, you are able to see my slide now, sir.
Yes.
We can see your slides. Krishnakant was talking about his journey. So let us, in the meantime, as a stopgap, so let us give him 2 minutes to complete his point he was trying to say.
Okay, sir. Okay, sir. No problem. No problem.
Yeah.
Yes, sir. Actually, sir, I was working with Shiv Narayan, sir, regarding this FSS technologies. And I did my PhD with Dr. Raghavan at NIT. So currently I started working with Dr. Prasad at ADA for real-time exposure, and I'm doing something real-time now. I joined recently, and it's a very good opportunity for me to learn and work with real-time applications for Indian defense systems.
Very good, Krishnakant. Congratulations for your new appointment. Even
Thank you, sir.
though I came to know from some other sources. Very good. Congratulations to you and also Professor Raghavan. And I wish all the best for your all future endeavors. So let us
Yes.
go ahead.
Are you speaking in Telugu with Dr. Prasad?
Yes, sir.
Krishnakant?
Sometimes Telugu, sir. Yes, sir. We are talking, sir.
So where are you from? Native place?
I'm from Andhra, sir. Kadapa.
Oh, Kadapa. Wow, you have to be careful.
No, sir.
The
No,
guys
nothing.
are known for bombs.
No, sir. We are very polite.
Stealth technology.
Right.
Thank you.
Thank you, sir.
Yeah. So, Dr. Shiv Narayan, you may please start the proceedings again. You can go back to where you are.
Okay, okay, I will start now. Okay, Professor.
Please. Yeah.
Okay. So, so sorry to all people actually, because of the current has gone here. So because of all disturbance has come. Anyway, I will pick up again where I left from the 19th slide.
Did you have FSS on your
Requirement
window?
of
Hello.
the modern airborne radome.
Shiv Narayan.
So,
Do you have FSS on
modern
your window?
airborne radome requires superior power transmission efficiency over the specified frequency band. Basically, it is more than 90 and 95%. And the EM performance should be stable with respect to the angle of incidence as well as polarization, and it shows the minimal distortion, phase distortion, and fast roll-up characteristics outside the operating band. The main why we are using for the FSS, the main drawback of the monolithic radome that degrades the performance within the specified frequency range. Also, the performance is very sensitive to the angle of incidence. The possible solution is the FSS based radome. So here I will give one example of the FSS radome, that is advanced FSS. Actually, one of the structures is there, like here we have used one Jerusalem crop outside the single square loop. Here the single square loop resonates at low frequency and Jerusalem cross resonates at the high frequency. So both combined and show the band pass characteristics, whatever it is shown here. So if you see here, we have plotted for 0, 30 and 60 degrees. So frequency is stable with respect to the angle of incidence. So it show more than 90% transmission from 10.2 to 11.2 gigahertz. So these structures we can use for radome application. We have done for TM polarization also, if you can see. So TM polarization also, it show the stability. Now we have used these FSS structures into the radome structures. So we have embedded into the monolithic radome exactly into the mid plane of the radome, so that we can get better impedance matching from both sides, and it will allow the signal without any with minimum loss. So the we have designed the radome wall at 10 gigahertz. The thickness of the radome wall has come 10.8.848, and dielectric properties we have used quartz, that is epsilon r 3.12 and 0.001. 0.01 is the loss. So we have done the EM analysis for this. So if you see here, whatever right side is the red curve shows the FSS embedded radome, and it shows a flat band pass as well as sharp roll-up characteristic as we are going from the X band outside. But if you see blue curve, whatever it is shown, the blue line, it is a monolithic radome, and it shows good transmission at design frequency, but outside the frequency band, and it degrades and there is no sharp roll-up characteristics. So this is the advantage of FSS over the monolithic radome. Now for proof of the concept, we have fabricated this structure and measured. So the measured result, whatever it is bottom side, we have shown the red curve is the measured result and blue one is the actually simulated one. Slight deviation has come because of the measurement error, and the whatever radome wall we have fabricated, it is just clamp the multi-layered structures. Now we got some confidence in planar structures, then we have gone to the semi-cylindrical radome. So in this case, we have selected single square loop, the single square loop, and whatever patch kind of structures we have just taken here. So we have uh, conformed the structures over the cylindrical surface. Then we have done mapping from planar to the conformal mapping we have done from rectangular coordinate system to the cylindrical coordinate system. In that way, we have calculated whatever r and theta is required for cylindrical, as well as length of the cylinder, that is equivalent to height of the cylindrical is equivalent to the L. So this structure we have simulated in CST and find out whatever this is the E-plane pattern. So right side, if you see the zoomed view, whatever it is there, the blue one, it shows the FSS radome, and the red color, it shows the monolithic radome. If you see here, with FSS embedded radome, we are able to enhance the performance from 0.17 dB loss to 0.10. So this is the advantage what we want. And same way we got for H-plane pattern also, from 0.18 dB to 0.11 dB we got with FSS. A proof of the concept, these FSS structures we have fabricated and measured. So in measured result also, whatever green color it shows, that's the antenna elan, the red color is the FSS radome. The FSS radome here also, it is giving better performance as compared to the monolithic radome. Now we'll come to the actual development of the FSS radome. How to develop the radome, whatever for the airborne application. So here we have gave some steps. First, we need to freeze specification that intended to be achieved during the projects. This is the first step. Second step, while starting the work, first we need to select the candidate radome material. What material we are going to use for the FSS embedded radome. Second and the last, actually, whatever is there, we need to select the suitable FSS structures. So, for example, we have set here the specification, like we want actually 8 to 10% improvement in the transmission efficiency as compared to conventional monolithic radome. And we require the improvement in bandwidth from monolithic conical radome to the 300 megahertz to the 500 megahertz. So this we have set the target, and to achieve this target we have started working on that. So first we have started with planar FSS radome. So actually for designing, we selected based on the several analysis of several kind of FSS structures. So we have selected cross slot so that we can achieve whatever we have set our specification. So cross slot we have taken into consideration, and we have embedded in the mid wall of the monolithic radome. So we have done first the EMS analysis, then we have fabricated the structures. So we have fabricated just for just to understand whether it is working or not at the planar level. Then we have made the size 350 mm by 250 mm, and for comparison we have made actually same size of 350 by 250 the monolithic radome. The thickness of radome is optimized to be 7 mm, but the fabricated one we got close to 6.51 to 6.81. Monolithic and FSS radome we got 6.41 to 7.1. Because of the fabrication error, some deviation has happened. And the material we have selected glass epoxy material for the fabrication. So with this, actually we have fabricated first the planar, and we have measured in the anechoic chamber at our NAL both FSS radome as well as monolithic radome. Then here we have compared the measured result as well as simulated result, FSS based planar radome. The left side, whatever here is there, the black color is shows the antenna elan, the measured pattern, and monolithic and FSS. So right side, if you see the whatever the zoomed version is there, the blue one it shows the FSS embedded, and red one shows the monolithic radome. So with FSS embedded, we could enhance the performance at design frequency from 1.33 dB loss to just 0.61 dB loss. So in this way, we got the advantage with FSS, and further we have validated the FSS radome measured as well as antenna elan and FSS radome measured and simulated. So we are getting better actually agreement between measured and well as simulated. Then we have compared the simulated and measured results at 9 gigahertz. So simulated, if you see, the transmission loss was 0.96 for the monolithic radome, and measured one we got minus 1.33 dB. That is slightly more in the measured case. And power transmission loss in FSS embedded radome, the simulated it was minus 0.5 dB loss and measured is 0.61. So we are getting close agreement with the simulated and measured for the case of FSS Radome. So in this case, we have compared between simulated and measured. So in the case of planar case, we got 13% enhancement in power transmission in FSS as compared to the monolithic, where we have set the target close to 10% because the 10% we have set the target for conical radome. Now, once we got the confidence of our configuration for planar case, then we have gone to the actual airborne radome like conical shaped FSS embedded radome. In this FSS embedded radome, and we have selected the dimension actually 535.5 mm and diameter is 337 by 68 mm. So we have with respect to the angle of incidence, because at nose of the radome the angle of incidence is the highest, that is 72 degree, and we have separated out the structures into the 3 to 4 sectors, that is from 65 to 72, 50 to 65, and 0 to 50 degree. And antenna, it is located at 25.5 mm from the base of the radome. And we have designed this FSS structures at 9.5, and radome material we have selected glass epoxy, whatever we have taken previous one. So we have done first the theoretical analysis. So in theoretical analysis, we have done at center frequency 9.5 and band edges frequency 9.2 and 9.8 gigahertz. If you see at 9.5 gigahertz, so the blue color curve, it shows the FSS embedded, and red one it shows the radome embedded, monolithic radome. So as compared to the monolithic with FSS, we could enhance the performance from minus 1.1 dB to minus 0.7 dB. And same we got the enhancement into the band edges frequency at 9.2 and 9.8 gigahertz. Now we have compared in this table, and whatever we got at edges frequency, center frequency as well as band edges frequency, like 9.5 also we are getting enhancement as well as band edges frequency also. So we have compared this actually whatever we have done the simulated one. After the simulation, because whatever radome is there, it should not qualify only for electromagnetically, it should qualify with respect to the environmental condition as well as structural way also it should qualify for the aerospace application. Environmental study on FSS based planar laminate. So we have taken 25 by 25 mm travel coupon. Then we have kept the actually material for 24-hour specimen were dried and hot oven to get the constant weight. Then travel coupon and mechanical test specimen were conditioned at 70 degrees centigrade with 85% humidity in the temperature humidity chamber. And then we have compared the moisture absorption curve for FSS planar laminate in case of FSS as well as in the case of monolithic. So in the case of FSS, the moisture absorption, whatever FSS structure is there, it is less, that is 0.65% as compared to the monolithic, whatever that is more. So in this case, FSS embedded structure is safe in terms of the environmental. Now we have done the study, whatever the structural way, how it is to estimate the layer wise stress and strain level on FSS composite canonical radome under uniform external pressure. And also we compare the strain value on FSS layer with the allowable strain limit specified from the EM design to find the buckling factor, buckling behavior, and to estimate the buckling factor of the radome for uniformly distributed extended external load. So in this case, what we have taken for 7 mm, whatever radome wall is there, so we have taken actually like 16 layer top and 16 layer bottom, and FSS layer it is 30 micron we have considered. It is taken into the mid portion of the monolithic radome wall. So we have done the all analysis like stress and stress analysis we have done by considering all the glass fiber mechanical properties as well as copper mechanical properties. So we have used the Nastran solver what is available at our NAL for the finite element analysis. So we have done displacement plot, normal stress plot of layer 1 in the longitudinal direction and normal strain plot of layer at the 17th layer, what is the FSS in the longitudinal direction of the whatever fiber is there, whatever we are using. Fiber means glass epoxy. So the maximum stress in the glass fiber we achieved actually 4.1 while 4.1 MPa, while allowable is 380 MPa. That is very, very high what we are getting. And maximum stress in the copper material we got 10.7 MPa as compared to the 7 MPa that is allowable. And maximum stress in strain in the copper material we got 0.000264 while allowable is 0.05. It is much higher. So the with extraction analysis what we got, whatever value with FSS embedded radome have, it is much less whatever it is allowable. So in this case FSS embedded radome structure is safe in terms of the aerospace application. When we got the confidence from electromagnetic, environmental as well as structural, then we have given the whatever freezed parameter is there to our fabrication group. The fabrication group has fabricated FSS embedded monolithic radome at our NAL. So we have fabricated and we have measured. So if you see here, whatever this table is there, this is the monolithic simulated transmission loss. That is, we are getting close to -1 dB from 9.4 to 9.7. So here we are getting close to 300 megahertz bandwidth. If you see the FSS simulated as well as measured one is there, it is showing from 9.2 to 9.8 gigahertz, whatever we are getting around 1 dB loss. So only the difference is the slight deviation is there with respect to the resonance frequency close to 100 megahertz. The reason behind it, the first time we have attempted at our NL, and also whatever FSS we have embedded slight deviation in the periodicity and the layers, so we got deviation. But we got the transmission bandwidth with respect to 600 -1 dB loss in FSS, the 600 megahertz. We can see here in this graph, the red color it shows the FSS embedded radome, and whatever black color it shows the monolithic radome. So FSS embedded radome, it enhances the performance at center frequency as well as the bandwidth. So in this way we got 10 to 12% enhancement in the transmission as well as bandwidth we got from 300 megahertz to 5 to 600 megahertz. So in this way we are very close to the specification what we have set the target before starting the work. So this is the procedure how we go through for the FSS radome, how to design and develop. Recently metamaterial structures has come into the picture where this is getting used for high performance of FSS radome, because the metamaterial structure can be used for millimeter wave application, as well as with metamaterial we can easily achieve multi-band as well as broadband configuration. So metamaterial element based FSS, why requirement is there? Because modern unbound radar system requires superior EM performance characteristics over wide frequency band, and radome should have the stable characteristic with respect to the angle as well as polarization, and radome having broadband multiband characteristics as millimeter wave and microwave. So because millimeter wave radar also has come into the picture, so to work the FSS radome at millimeter wave, the metamaterial structures will be more preferred compared to the conventional FSS, because conventional FSS shows more losses as millimeter wave and optical frequency region. So here we have introduced new structure here like a swastika shaped tightly coupled metamaterial structures. So here two swastika shaped structures are superimposed, and they are both are opposite to the dielectric material. And these structures we have studied the permittivity and permeability. The permittivity it shows around 8 gigahertz and 16 gigahertz. Permittivity negative we got around 8 gigahertz. Permittivity negative we got 6 gigahertz and close to 16 gigahertz. And we can also understand this with the transmission curve, whatever at 9 gigahertz, whatever we are getting, it is due to the electric resonance, and 5.2 whatever resonance is coming, that is due to the magnetic resonance, and 13.66 we are getting due to the magnetic resonance at 13.6. We can understand better way here whatever this electric resonance and magnetic resonance at M1 and M2, whatever happening with the current distribution. So electric whatever magnetic resonance occurs due to the asymmetric current distribution at 5.18 into the lateral arm of the structures, and symmetric current distribution at 9.13, that is the electric resonance occurs due to the symmetric current distribution, that is shown in figure B. And resonance whatever FM to 13.74 gigahertz, it is happening. This is due to the asymmetric current at the lateral arm, whatever S arm is there, red color it is showing, because of that the current is there. For proof of the concept, we have fabricated the structures at our NAL, and then we have measured. So we are getting better actually simulated and measured result. Actually, we are getting very close to that. And after that, to achieve the radome characteristics, means actually to make this structure for radome application, we need band pass and sharp roll-up characteristic. If you see here, one sorting pin, one sorting strip we have added at the edges of the swastika shape. In this case, the first magnetic resonance, if you see right side permittivity and permeability response, the first magnetic resonance got disappear. We have now only one resonance due to the magnetic current, and one is due to the electric resonance at 7 gigahertz. So between 7 and 11 gigahertz, we have the non-resonance frequency region. So that is very much suitable for band pass characteristics. Now we have studied this structure up to the 60 degree with both T and TM polarization. So the structure shows very stable response up to 60 degree, and also it shows bandwidth from 9.5 to 10.8 gigahertz with respect to 0.5 dB loss. So here we are getting more than 1 gigahertz bandwidth with respect to 0.5 dB loss. And also for proof of the concept, we have fabricated these structures into our lab, and we got very good agreement between the measured as well as simulated result. And further we have studied these structures because metamaterial is known to work at millimeter wave also. The same structures we have optimized and designed for millimeter wave also. So at millimeter wave frequency, that is from 50 gigahertz to 75 gigahertz, and we got 5 gigahertz bandwidth around 64 gigahertz. So in this way, this structures is working. Structure is also working at millimeter wave frequency region. And now actually we'll come to the sorted swastika shaped tightly coupled metamaterial structures. So same structures we have embedded into the radome wall. So in this case, whatever radome wall after embedding, we have done the simulation with respect to the 3D ray tracing based geometrical optics in conjunction with aperture integration method. So here this is the radiation characteristic of AESA antenna. If you see right side, whatever the curve is there, with FSS embedded, we got just 0.125 dB loss, while monolithic is 0.4, and 0.254 is FSS without shorting. So with shorting, we are getting better performance as compared to the without shorting. And we can see here also co-pole power transmission and both side error. So co-pole power transmission at whatever sorting strip, it's so very stable with respect to the angle of incidence, and also without sorting also we are getting close to 0.3 dB loss. But actually whatever both side error is there, that is enhancing whatever metamaterial without sorting, that is the green color, that is the it is going more than 4 to 5 milliradian, while the blue curve is so below 4 milliradian. So in this way, whatever the metamaterial structures with the sorting strip, it is more better performance as compared to the other. This is overall about the Radome application. Now the second application will move to the FSS for antenna application. How the FSS structures is very useful for antenna also. Basically, the FSS structures is a whatever stealth is there, like a low observer platform requires low RCS antenna with high gain and directivity and compact and wide bandwidth antenna. This is the requirement for stealth application. The possible solution is FSS and metamaterial based antenna designed by FSS based high impedance ground plane. Due to band reject characteristic, it is used, and also FSS structure is used as super straight due to the band pass whatever nature is there. So here we took one example of like FSS as a super straight. So FSS band pass kind of FSS is used because here whatever the structure shows the band pass characteristic around 9.5 gigahertz. So at 9.5 gigahertz FSS we show as a band pass characteristic. At the same frequency we have designed the microstrip antenna also. So at this frequency this structure show the band pass characteristic, and because the FSS structure this collimate the beam and it enhance the performance like directivity. So we have done the analysis using transmission line theory and reciprocity theorem. In this case antenna whatever ground plane is considered as a short. So in this way we have find out the impedance as well as reflection coefficient of the FSS antenna aperture antenna structures. Then we have from reflection we find out the E plane or radiation pattern of FSS super straight antenna. So here we have done the validation, and this is the microstrip patch antenna loaded with FSS super straight. This is the radiation characteristics. If you see red and red curve, that is the E plane pattern of the antenna, whatever we have considered. So E plane we got 3.25 dB and H plane we got 3.3 dB. Whatever directivity is there. So we are getting the enhancements in directivity with respect to the FSS based super straight. Now second example we have taken how the FSS is useful when we are using the FSS into the ground plane toward the RCS reduction. So here we took one example like single microstrip antenna, and the ground plane of the FSS ground plane of the antenna we have removed the single square loop FSS. If you see here, there is no much variation in the radiation characteristic. If you see right side the monostatic RCS, the RCS of FSS based ground plane actually antenna, right side if you go beyond at 15 gigahertz we are getting RCS very low RCS as compared to whatever without FSS whatever antenna it shows. And the further we have designed the FSS based array, that is 1x4 array. So here we have used the FSS unit cell like miniaturized kind of element. So the ground plane of the FSS, it is the ground plane we have used this actually. At the top we have used the 1x4 patch antenna. So if you see right side, the radiation characteristic is almost similar, only slight loss is we are getting 0.1 to 0 dB loss, but we apart from that we are getting major advantage of RCS reduction. So we got monostatic RCS reduction up to 9 dB SM over the frequency from 2 to 20 gigahertz, and also we got bistatic RCS reduction also up to the 5 dB SM over 2 to 18 gigahertz. And further the RCS reduction of patch antenna array with FSS ground plane. So here we have done the active RCS calculation. So in this case, specular radiation mode RCS, whatever it is there, means this was the structure RCS, and radiation mode RCS also we computed with the same structure. So here if you see whatever blue curve is there, this is the PEC based ground plane, and whatever red color curve right side is there, that is the FSS based ground plane. So we are getting whatever radiation mode RCS also we could reduce by embedding the FSS. And now we'll come to the hybrid element FSS based structure, that is the active FSS. So this kind of FSS, it is used to reconfigure the antenna configuration, whatever antenna operation is there. So in this case, if you see, so outside there is a square loop, inside there is a Jerusalem cross, and pin diode is added between Jerusalem cross and single square loop. Whenever diode will be on, in that case, Jerusalem cross will be shorted with the single square loop, and full structure will behave like a single structure. So in this case, the blue one curve, it is like a full reflection kind of structures. And second one, if you are switching off the diode, in the switch of the diode case, the FSS outer whatever single square loop and Jerusalem cross, it will resonates at different frequency, and combinedly it will show the band pass at 10.4 gigahertz. So in this case, by switching on and switching off the diode, if you are switching on the diode, it will reflect the signal back. If you are switching off the diode, it will allow the signal pass through it. Now we have simulated this structure. If you see the result, and return loss slightly it is degraded, but still it is minus 20 dB, it is better. Radiation characteristic is also, there is no difference in that. But if you see the RCS estimation of the structural RCS of the FSS based microstrip patch antenna, if you see, whenever we are switching off the diode, in that case it allows the signal to the pass across the antenna, and also it will not allow the antenna to radiate, but it will reduce the RCS close to 23 dBsm at the operating frequency band. So this is the advantage. And whenever diode is on, in that case antenna will work like a normal antenna, because FSS will reflect all the signal and it will work like ground plane to the antenna. For proof of the concept, we have fabricated similar concept, and we got the measured whatever result is similar whatever we have proposed. And some challenges are there whenever we are using the FSS based antenna. The main is there, the FSS based HIS based antenna whatever is faced for the weight penalty due to the requirement of dielectric support in the design of FSS based HIS. And also FSS superstrate, if it is very close to the antenna, there will be mutual coupling between the antenna array and the FSS. So in that case, we have to do very proper way, we need to do the calculation as well as spacing between the antenna array and the FSS, so that mutual coupling should be minimum. It is also challenging to estimate the mutual coupling between antenna array and FSS array. And moreover, wherever RCS estimation we do for finite based FSS array, then it become more computationally intensive. Sum of whatever this is given in our paper. The last application is the frequency selective surfaces for radar observing structures application. Like FSS is very useful for radome application as well as antenna application. This is also very much useful for the radar observing structures. The requirement of SS based radar observing structures, because thin conventional RAS whatever previously it was getting used generally exhibits narrow band absorption. The broadband conventional RAS example German and Dallon are usually thick and bulky if you are designed with that. Ferrite based observers are quite heavy in the weight. So that's why necessity of thin and broadband observer in modern aerospace industry, including stealth platform, it is essential. So the possible solution, we can design such kind of thin and broadband using frequency selective surface and metamaterial based RAS. Usually thin and lightweight, because we can design thin and broadband, we can design, that's why we are using the FSS. Here we have given like a typical FSS based radar observing structures. So how to design, here there will be ground plane and there will be spacer, and top of the dielectric we have to print the resistive kind of FSS in such a way that whenever wave incident upon it, it shows the impedance matching with the free space wave, and it will allow the signal to pass inside. Once the signal will pass inside, and while coming back whatever signal is there, signal how it will go other side, then it will see the impedance mismatching, and finally the wave will go back and forth between dielectric in the ground plane as the FSS, and finally it will be observed. So this is one another example 3D view of the FSS RAS where single square loop is taken. Basically, in terms of the equivalent circuit model, the frequency selective surfaces, the equivalent circuit, whatever resistance due to the ohmic laws because of the resistive nature, inductance and capacitance. So R1, L1, C1 we make in such a way that the impedance of FSS should be the equivalent to the free space. In that case, it will allow the signal to pass across this and it will absorb the maximum signal. So using the FSS, we can design two-way the radar observing structures, narrow band as well as wide band. The narrow band is only associated with the structural resonance of the FSS structures. So this is not very difficult. Simply we can design the way we want. Actually, this is the theme. But whenever we are going for wide band radar observing structures, so in this case, choosing the suitable thickness of the dielectric slab to generate the second grating lobes. So in this case, thickness we need to select in such a way that we should be able to dominate the higher order harmonics. So in that case, we'll get one more resonance at higher order frequency region. So in that case, we'll get broadband. So how to get if the inductive reactance of the FSS structure equal to the capacitive reactance, then it will your second grating lobes will generate and will get the broadband. And for designing the FSS radar observing structures, the optimization is also very important parameter, because optimization play a very important role while designing the FSS RAS. We have taken one example here, optimize FSS RAS like genetic algorithm we have used. So in this case, the dielectric whatever we have taken like a cross kind of dipole, and this is a single layer. So if you see right side first curve whatever it is shown, so for better bandwidth we have optimized this. So with based on genetic algorithm optimized, it show 14.4 gigahertz bandwidth, while non-optimized show just 12.6 gigahertz. For better absorption level, whatever blue curve is there, it shows minus 10 dB return loss, while absorption return loss, yeah. And whenever we are optimizing the structure, we could achieve 15 dB. So this is the advantage of optimization. So for proof of the concept, we have designed the prototype and we have fabricated and we have tested, we got the similar whatever pattern. Now development of EM characteristics of the radar observing structures. So, and the same way, whatever radar observing structures properties, there like radar observing materials are there, like carbon black is there, carbon nanotube is there, graphene based RAM is there, simple ferrite RAM is there. These are all material we have developed at CSIR NAL to achieve whatever absorption is there from 2 to 18 gigahertz. So in this case, this sample we have fabricated at our NAL and tested also a different band of the frequency. So here what I want to show, here I want to show how the FSS structures can be used to enhance the performance of radar observing material. So we took one example of carbon black polymer radar observing structure. So we have printed the FSS single square loop FSS over that, and we have done just analysis and see that whatever here blue curve is so is the radar observing material, that is the carbon black with 3% carbon black. So here we got 3.3 gigahertz bandwidth with respect to minus 10 dB. But whenever we have printed the FSS, we could enhance the performance from 3.3 to 7 gigahertz. So this is the advantage. The FSS, what FSS did here, it did towards the impedance matching with the free space. So that's why we got better performance. So this is overall whatever the talk what I have with me. Now we have some facility with us to support the FSS activity. We have some workstation, commercial software package. We have FICO. Now we are going to purchase HFSS also. Software package we have developed at CSIR like Redent Code we have, Abrita we have. And for fabrication we have prototype etching machine, free space measurement facility and anechoic chamber. These are all the manpower whatever who supports the all EM whatever FSS activity is going at our NL. So these are my team who work with me. We work along with us. And this is overall my presentation. Thank you to all audience who is listening actually patiently my talk. Thank you once again.
Thank you, sir, for such a wonderful, informative talk. You have put
Okay,
everything.
thank you.
You have put everything from theory to practice, sir. We are very,
Yeah, I tried my best.
happy and proud
Yeah.
to have a speaker like you. And your
Anu, you are not audible. You have to be loud.
lab is having and your strength. And the work you associate with DRDO, ISRO, and other agencies, along with reputed industries, will help us towards indigenization of this defense application side.
Sure, sure. We are trying to indigenize many
Sir,
technology.
There are a few couple of questions from the audience.
Yeah, sure.
Shall I take the question, sir?
Yeah, yeah. Can you speak loudly, sir? Because in mobile it is difficult.
Yeah. I also hear very feeble voice from Anu.
Yeah, please, can you, if you increase your voice, it will be good for me.
Okay, sir. Sir, can you hear me?
Yeah, now it is fine.
Still not loud enough. Not loud enough. Increase your system volume. Yes.
Sir, are you able to hear now, sir?
Yeah, it is fine now.
Yeah.
Okay, sir. We are very much happy to know the facilities your lab is having, and we are very happy that we got a person like you for today's session. And in fact, the first two sessions were very wonderful, informative, and whatever theory are there in the book, you all have put that into practice. And these kind of association with DRDO, your organization association with the DRDO, ISRO, and other agencies will definitely, and along with the tie-up with the academic institutions, will help us towards the indigenization of the defense applications. And there are a couple of questions from the audience, which I'll tell you, sir.
Sure.
Yes, sir. Some question is there where I am coupling those questions. Whether FSS and meta service are same, and how FSS is acting as a filter. And together with that question, in case of antennas, if FSS is working as antenna, how it affects the return, how to mitigate that, and how you are calculating the reflection coefficient based on the dimensions. So these questions, first question is how FSS and meta surface are they same?
Okay, one by one we'll go ahead.
Yes, sir.
So see, actually whatever FSS is there, FSS has started very long back during 17 and 80s when there was no metamaterial. So metamaterial come into the picture after 96 after Pendry and Smith work, and from 2000 the metamaterial has come actually more advanced way into the world. So previously whatever FSS was getting used, so because that FSS structures won't show the negative characteristics into the frequency region, whatever it is there. So we call like a conventional FSS, we can say the FSS. The meta surface is a two-dimensional metamaterial, because whatever metamaterial is there, metamaterial is three-dimensional, also the two-dimensional. So the meta surface, whatever it is two-dimensional print is there, two-dimensional structure, we call the meta surface. And if meta surface behaves like a, then we can call meta surface also the frequency selective surface, because frequency selective surface is a property that we can achieve with two-dimensional arrangement. So that two-dimensional arrangement we can achieve with conventional structure also, with metamaterial also. If we are getting with metamaterial, then we call meta surface, whatever. So basic difference between meta surface and FSS is only the negative characteristics, because meta surface show the negative characteristic into some frequency region and conventional FSS doesn't show. But we can say meta surface also the FSS if it shows the filter characteristics. So this is as per my view whatever differences are there. And now we'll come to the second question, whatever you have asked. It was related to
antenna, FSS as antenna, and how it is affecting the return loss and how to mitigate that. If
yeah. See, whatever FSS is there, so because antenna, actually there are two cases we use mostly for the antenna application. The first is we can use the FSS into the ground plane. Ground plane we are using, and we can use at the top whatever surface is there, because FSS is also actually it shows the filter characteristics when wave actually interact with that. Because if you are using normal FSS, actually microstrip antenna, so we use the ground plane. So in the case of ground plane, whatever return loss is there, it will fully reflect the signal. But in the case of FSS, some design, whatever, if you are not designing properly, so some wave will leak from the FSS also other side. So in that case, return loss of the antenna will not be that much good, whatever your FSS without FSS is there. So we need to design proper way, whatever FSS. The main reason how to enhance the performance of return loss of the antenna, basically the whatever FSS design is there, it has to be designed at the same frequency at what frequency the antenna has designed. And also because we are using in the ground plane, some frequency shift also comes because of the thickness of the antenna. So that also we need to take into account, so that the frequency at which antenna is operating, the same frequency the FSS should reflect the signal. So in that case, return loss we can achieve what we need. So return loss will not actually degrade in that case, as per my view.
Sir, one more question is there. Like you were talking about the Sostiga structure for MTM based FSS.
Anu,
So how,
again you are very feeble.
Sir, sir, you are talking about that Sostiga structure for MTM based designs. You are
Yeah, it's a well question. So whatever dimension is there for hello, are you able to hear me?
Yeah, we can hear you. Please go ahead.
Yeah. So actually, whatever swastika shaped structure is there, we have made the equivalent circuit model in this paper, in this presentation. We have not actually shown the equivalent circuit. Based on transmission line model, we have designed the equivalent circuit based on the dimension. So unfortunately, in this presentation, I didn't show the equivalent circuit model what we have actually derived for this swastika shaped structure. So from the equivalent circuit model, we can easily calculate whatever actually with respect to the frequency, what frequency we are going to design, we can calculate whatever dimension is there. So it is there in paper. If you can go and download, then you can get it.
Noted, sir. And the sir,
yeah, any other question?
Sir, one more question is there. Some couple of questions are still there, but if you future our
sure. I will. You can take from Professor Saha. Professor Saha, he has my email ID.
Okay, sir.
So I just have a quick comment. You had a very nice presentation.
Sir,
and you covered.
Excuse.
Yeah.
You want to say something?
Yeah, please.
Sivada, you have a query. Yeah, go ahead.
Yeah, please go ahead. Please go ahead.
Yes, sir. So my question is, like, have frequency selective services ever been used practically for Radome application, like practically implemented since ever?
Yeah, definitely. Actually, in our NL, we are going to design practically whatever that FSS based radome. I have already shown one conical radome actually in my presentation. So we have realized at our NL, the size is 500 mm, 50 mm height, actually 380 diameter. We have already realized at our NL. Now we are going for actual, actually for flight worthy, actually we are going to make in the future. Soon actually we are going to do the design.
Sir, like in is that tunable? Like,
Yeah, ma'am.
sir, I meant tunable type.
Yeah, tunable type also you have to integrate whatever active actually devices you need to integrate along with the FSS structures. But tunable kind of FSS structures for aerospace, it has some constraint because if you are going for active devices embedded into the FSS, so if you are going for aerospace application, some difficulty you may face because we have to make actually circuit for exciting the whatever this pin diode and whatever diodes and all these things if you are using. So you can design a tunable also, madam, for planar structures, and there is a good no problem.
Thank you so much, sir,
Yes,
for the
sir.
wonderful presentation. So now
Okay, thank you.
Thank you, sir.
Sir.
And now I hand over the virtual to Saha sir for his comments.
Yeah, thank you, Anu. Yeah. So I was just trying to have a technical comment from Dr. Shiv Narayan after nice
Yeah, please.
presentation and covering almost 60-degree azimuth as far as the FSS applications are concerned. So my comment
Yeah.
that I would like to hear from you is like metamaterial. FSS is also have a bandwidth limitation because these are typically narrowband applications. So some efforts are there to make it dual band and broadband. But
Yeah.
if we really want to apply it for a little bit high band applications, so what are the approaches one should attempt? So that is the comment that I want to hear from you.
Yeah. So we are working towards by increasing the bandwidth of the FSS embedded structures also. So there are two way what I can comment on that to enhance the bandwidth. First, we can do like a cascading kind of FSS, means two or more layer of FSS if you are embedding, if you are using. So we can enhance the bandwidth in that case. And also whatever requirement is there nowadays, we can achieve flat band pass response as well as sharp roll-up characteristic we can achieve if you are going for multi-layer kind of structures. So that is one. Another one is also there, if you are smart enough, if you are able to design um, uh, uh, more than one element over one structure itself, over one plane itself, like multi-element kind of multi-element FSS. So
Right.
in that case also we can achieve multi-band as well as broadband also. So this way actually we can achieve,
Yeah.
and more important what I can say, whatever FSS is there, there are two kind of resonance is there. One is due to the structure resonance because of the electrical dimension of the structure resonance comes at one frequency. If you are able to actually whatever excite higher order harmonics with the same strength and that, then we can achieve one more resonance at higher frequency region. So in that case also we can enhance the performance, means bandwidth, whatever.
But that higher order frequency is not controllable, right? Once you decide the
Yeah, actually to enhance the higher order harmonics, so we should have very good control over the structure. So suppose normal structure is there, which way we need to add some more element with that structure so that we should be able to enhance the actually desired actually higher order harmonics. But this is slightly difficult process, how to enhance actually.
Yeah. You are,
Yeah.
rightly indicated because some of the people are trying to use FSS for some upcoming applications like energy harvesting applications and other things. That yesterday Dr. Rao was having on FSS based structures limitation in connection with some losses, especially when we use for Radome applications. So do you have
Yeah.
any comment and experience adding that?
Yeah, actually, whatever FSS is there, see, with FSS, whatever inherent losses is there, that we cannot actually reduce the inherent losses, but the what advantage we can achieve by increasing the bandwidth, we can stable the losses, like whatever if we, because we are from the Radome background mostly. So Radome, if some Radome is working at 9 gigahertz, let us say, so with FSS, we can increase the band, like at 9 gigahertz, suppose if we are getting 0.5 dB loss, so we can increase the range of the losses, like 0.5 dB straight way we can achieve from 9 to 9.5 and 9 to 10 gigahertz. So in this way, advantage is there, whatever FSS is there, and also losses in the material up to some level we can achieve by embedding, because FSS also works like impedance matcher.
Yeah, yeah, right. I understand. So yeah.
Well,
Very
I think Chinmay, I think your question is, my comment was yesterday for the dual band S and
regarding after
S and KA band.
yeah, I
So
think
for
after
those applications,
Dr. Sagi's presentation.
yeah, for those applications, FSS is not a good thing because technology is there for a dual band free technology. So why adding additional FSS, suffer the losses, and then there are other things like
Yes, sir.
loss and other things. So for those applications, it's not a good thing. So we try to avoid, but for radar applications, it's a very good thing.
Yeah.
Because it's a must actually. Nowadays, I think there's a lot of noise and interference coming from the ground. So sometimes you have to, we have seen actually 2 or 3 frequency bands we need to suppress
Yes.
part of the radar antenna. So I think those things are very challenging. So that definitely you have to use the FSS. But tunable
Yes.
FSS, I don't think is a good idea because it has it affects the losses and also it has impact on the radar cross section. So I think maybe in future if you reduce the losses, but right now
Yes.
passive FSS is the way to go.
Right. Yeah.
Yes, sir.
So thank you, Dr. Rao, for nicely chipping in and having your comments. The future, we'll see which directions this tunable FSS goes, because in certain areas, some people are trying to do good work in that area.
Yeah.
What comes in next few years? So any other people wants to have any comment? Anyone else? Okay, so then we can only close this. May declare have in the evening.
Yeah, I'll be available
Once
now.
again,
Current has come, then now there is no problem. I'll be available.
Yeah. So evening, as I told after, please be there. The evening session start at 5 p.m. with talk by Dr. CJ Reddy, which will be followed by another talk which will be shared by Lars and Lucia. They are from Italy. And immediately after that, we'll have a very thematic panel discussion, which will be enlightened by all the speakers, along with President-elect Professor Antar, IEEE Chapter Activity Chair, Dr. APS Chapter Activity Chair, Dr. Poddar, and Art and APS Coordinator, Dr. Siddiqui, and some of our colleagues and fellow officers, of course. So, in all of you, and of course with the panel discussion which start 8 p.m., which will be followed by the valedictory session.
Okay,
So
sure.
Shivada, you may close this session.
Okay, thank you.
Thank you, Dr. Shiv Narayan.
Thank you
Love
once
to see you.
again, Professor Saha, Dr. Sudhakar Rao, and all the audience who is listening my talk actually with patiently from last 1.5 hours. Thank you all.
Thank you. Take care.
Okay, thank you.